Hi, this is the second or third class. Yeah, third class of the D class, which is dealing with probability. This is chapter 2. So I already heard that you learn about the definition of probability as well as rules of probability and Bayes theorem. And today in this D class, we are only dealing with the definition of probability, uh, in particular, relative frequency approach. So another type or another concept will be taught by Professor Park in video class maybe. So as you already know, there are representatively two kinds of getting the probability. The first is classical approach, which is which is in which we get the probability by dividing the number of the event divided by the number of elements of the sample space. So this is very classical approach, and we can get each probability academically. Or we, I think we can also get the probability by using this approach, which is a relative frequency approach. So by counting all the number of the event happens divided by the total number of trials. So it is more like in real life. So we can count all the number after we repeat the same experiment very many times, and we can also get the probability by using relative frequency approach. So you can see this graph that saying that uh, as we increase the number of the trial, our relative frequency is getting closer to a certain value, which is 0.5 in this case. So uh, this table also says the same thing. So as we increase the number of trial, our relative frequency goes to some certain value. In this case, so it implies that as we increase the number of trial, we can get some exact relative frequency probability, maybe. But it will be, yeah, derived later, actually. So let's just keep in mind for this time. And for today, we are only dealing with this part, relative frequency approach, because for getting the relative frequency approach, we have to repeat or we have to iterate the same experiment very many times and count the number of event A that happens. So actually, our programming can help us to do that. So this is why we are using our programming in this TA class for getting the relative frequency approach. So yeah, this is actually chapter 2 our file, and I will start from the beginning. So what you're going to do today is just getting the each value and getting the probability by using the relative frequency here. And before that, there is a for loop here. And I think I have to teach you about this R grammar. And actually, for loop is hmm, let's say that without for loop, we want to print for the I value, which is 1 through 10. Then we print 1, and then we print 2. And let's say that we did all the thing. And then we print 10 here. So let's say that we want to print all the value from 1 to 10, and then we can also do that by repeating the same function, print function, with different I value, which is 1 to 1 from 1 to 10. And if we run all this code, you can see in this below panel that we can get all the printed value from 1 to 10 here. But how about 1 through 100 or 1 through 1000, which is very, very burdensome for human, for us, because we are human, and we feel very difficulty. We feel very difficult when when we have to repeat the same thing very many times. Then actually our programming can do this instead of us. So with for loop we can do that. So this is the for, and the next grammar is in this parenthesis you can set a default variable, which is I, and I goes from 1 to 10. So this is actually vector, and it can be list or vector and anything. If you run this code, you can see that 1:10 is the same as the 1 through 10 and each integer. So it says that we are going to go through the I value from 1 to 10 in this for loop. So, and this is the command with this large parenthesis, and with this default variable I, we are going to print I. And as you already know, I goes from 1 to 10. So when you run this code, you can see that all the printed integer from 1 to 10. So how about 1 from 100? You can see also that all the value from 1 to 100 is printed here without any effort, because for loop gives us the exact value with the exact repeated value. And how about from 1 to 100, which is the 100 times, we are going to print high. Then you can say that high thing is printed 100 times, because from when I goes from 1 to 100, we want to print high strings in each I case. So it is printed 100 times actually. And how about summation? Let's say that we have a sum variable whose name is sum, which has a 0 value. And let's say that we want to get all the summation value from 1 to 100. And although we start with a sum which has a 0 value, uh, as we add the I value to the sum variable, and we store the value in some variable again, and we repeat this 100 times with different I value, and then you can see that some value has the summation of all the integers from 1 to 100. This is the R grammar for loop, which is very powerful when you want to repeat the same thing, or when you repeat the similar experiment as our own. And so let's start with our code. And as you already know, if we want to store a vector, which is a set of numbers, we can use the vector sign here, which is a C with the parentheses. So, and we store the vector in our own variable s. And so if you run this code, you can see that S has 5 numbers in as a vector. And this sample function gives us the random sample from our sample space. And the size argument means the number of the random sample. In this case, we are going to get one number. And replace is that there is two kinds of sampling. So the first is sampling without replacement, and the other thing is that the sample with replacement. But because we are not going to replace the using the replacement, we have to turn off the replace argument as a false with a false option. So because we have to repeat the same random sampling in this random sample space. So I think I omitted the explanation. Actually, in this case, we are going to roll a dice, which has five numbers, which is 1 through 5. So, and then we are going to get the probability where number 5 uh, occurs in this sample space. And as you already know, if you use classical approach, if you use the subjective approach, you always know that you already know that the probability is actually 0.2 because the sample space has 5 elements, and the probability that number 5 occurs or number 5 appears when we roll a dice is 0.2 because the number of the event element in event space is 1. So 1 divided by is actually 0.2. So I believe that we will also get the very similar number for our relative frequency. So because we are dealing with the dice, which is 5 numbers, we set the sample space with the 5 numbers with the vector and store it in our own variable S. And we want to random sample, which is same as we want to roll a dice with a sample function in this sample space and just 1 times without replacement. So if you run this code, you can see that the sample function gives us the value which is 1 from random sampling. It means that we always get different value from random sampling, but it can be also the same as the previous one, but because it is just random sampling, it gives us the sampling very randomly, so from 5 values here. So as you run this function many times, you always get each value from the sample function. So you can see that the first time the sample function gives us the value 1, and the next time value 3 and 5, which is different from each other. Although I repeat running the same function here, and it gives us the value 1 again because it is just gives us the random sampling number without replacement. So, and because we want to repeat the same experiment very many times, we want to use this is the time we have to use the for loop. So after setting the number of tires here, which is 100,000 in this time, and let's say that we want to store each result from our own repeated experiment. So for storing, we have to set the empty list by using the repeat function. So this function gives us the list, or gives us the vector uh, which is full of this x value in this time, which is a non-available thing, which is the same as null, and n times. So if you check E, we can see that E is a vector or list, which is a 100,000 NA value here. So we can store each repeated result of the result of the repeated experiment. So if you want to store all the result from each experiment, we can start with I is equal to 1, and after getting the random sample from our sample size, we store each result of the sample function in our i's index of the vector E. So let's say that I is 1, and after getting the random sampling from our sample space, and store it in the i's location of vector E, which is first location here because we already stored the I as a 1. And after running this code, you can see that vector E has a number 5 in first location because we stored it in the first location with this code. Or how about I is 2? Then you can see that vector E also has the number 3 here because we store the result of the sample function in the second location of vector E. And we want to repeat it through I 1 through 100,000, but which is very burdensome. So yeah, it is very, very not good in this case. Then this is the time we have to use the for loop. So we are going to iterate the default variable I 1 through n, which is 100,000 in this case. And in with each I, we are going to store the result of the sample function, which is a random sampling from our sample space, in our i's location of vector E. So we can fill out all the vector E with our random sampling from 1 through n, which is 100,000. So with this code, you can check that our vector E has all the random sampling numbers, which is the each result from the sample function without replacement. So we got all, actually it means that we repeated the same experiment 100,000 times very easily. So yeah, that's it. And we want to count, or we want to get the frequency that number 5 occurs in this case, because it has a lot of numbers here. Then we can use if else function. So the subject is E, and this is the condition. The first argument is condition that if E is equal to 5, we replace it with a 1 value 1. If not, we are going to replace the value with 0. So with this function, and store the result into our new variable, which is E underbar 5. And then we can see that all the value in vector E is changed into all the 1 or 0 value in E underbar 5 vector. So it means that if the element is 5, it is changed into 1. If not, it is changed into 0. So this time what you have to do from now on is just getting all the frequency of one value in e underbar 5 vector. And if you see, actually it is same as getting the mean of e underbar 5, or it is the same as some e underbar 5 divided by the number of trials here, which is same as the relative frequency. And you can see that it is 0.2. And it is same as getting the mean. Yeah, it result is the same value with the previous one. So you can say that the relative frequency with the relative frequency approach, the probability of uh, the event that number 5 occurs when we roll a dice, which has a 5 numbers, is about 0.2011, which is very similar to the classical approach, the result of the classical approach or subjective approach. So we could get the probability by repeating the same experiment very many times by using the for loop with the help of the for loop very easily. So I think I also have to check that if we can if we really get the closer value to 0.2, let's say that we moderate this n value, which is 100, and let's certain it. And so we can control the number of trials here. Let's say that we have a 100, we want to repeat the trials 100 times, then we can see that the mean value, the probability of 5 in n trials is 0.24. Or how about n the trial is 10,000, then if we run all the code, we can get the probability as 0.203. And how about the number is very bigger than previous thing, and you can get the it takes time. So it gives us the value which is the much more closer to 0.2, which is 0.200276. So you can see that as we increase the number of trial, which is n, we can also get the closer probability to the 0.2 actually, which is the same as the result of the classical approach. So in this case, we can realize that if we increase the number of trial, we can get the closer value to certain value for our relative frequency. So this is the end of the class, and if you have any question, do not hesitate to contact me, and see you again.